Welcome back. I guess it's always the case that once you do something, you see how you could do it better. So I'm making a bonus video here about how to derive the error for the algorithm for computing the natural logarithm. And this explanation will not involve a series argument. So you should be able to understand this argument with a good understanding of pre-calculus. Okay, so remember the input here is x, and we're trying to compute natural log of x. And so what we do is we rewrite x as a product, 2 to some power, 1.1 to some power, 1.01 to some power, and so on, where we're computing these powers. Okay. Here's the idea. Once we compute the first power, we stop the algorithm when multiplying by an additional 2 takes that number over x. So 2 to the correct power is less or equal to x, which is less or equal to 2 to the power plus 1, or 1 additional multiplication by 2. That's too big, so this is the power we're going to use. So we have this inequality. Then we compute the correct power on 1.1. So a1 is the correct power if a1 plus 1, or an additional multiplication by 1.1, creates a number which is larger than x. Okay? We compute the exponent on 1.01 by stopping when an additional multiplication by 1.01 creates a number which is larger than x. Okay, so we do this in general. Okay, if we go to 1 plus 10 to the minus k, let's say that k is like 4, so a 10 to the minus 4 plus 1, then I have 2 to the a0 plus 1.1 to the a1 plus 1 plus times 1 plus 10 to the minus k to the ak. That's between x and the same thing times 1 additional 1 plus 10 to the minus k. That's what would happen when we go out to that number. Okay, now let's take the natural logarithm of both sides of this inequality. We need to be careful when taking functions of inequalities, but all three things here are positive, so we can take the natural log, and the natural logarithm is an increasing function, so it's order preserving, and I don't need to switch the inequality symbols or worry about that. Now, if you don't understand that, be careful in your math class. Okay. Okay, but this is true then. So natural logarithm of this is less or equal natural logarithm of x. And then here, critically on the right-hand side, I've split the natural logarithm over this multiplication, so it creates an addition. I have natural logarithm of the first thing plus natural logarithm of this part, okay, with the additional 1 plus 10 to the minus k factor. Okay, now, here's the idea. The algorithm, what it does in the end is it adds this up. It applies the logarithm rules to this, and it computes a0 times log 2, a1 times log 1.1, ak, and all the way up to ak times logarithm of this, and adds that all together using the hardware constants as we learned in the first video. Okay, so this is actually the approximation that you're computing. Notice that it's the same thing over here. Okay? ln x is the real thing that you're trying to approximate, and so what we see here is your approximation is between is less than the real thing, right? But the approximation plus this term is greater than the real thing. Okay, so this is as far away as you can be from the real thing. So in other words, your error is less than or equal to this term, the ln 1 plus 10 to the minus k. Okay? Now, we need a little bit of something from calculus, but I'll explain it. This is less than or equal to 10 to the minus k. Well, why is this? If we draw the natural log function here, natural log x, and we draw this line x minus 1, we see that line x minus 1, they agree here at this point, 1, 0, but everywhere else, line x minus 1 is greater. So, function which just subtracts 1, which is what I've done from here to here, just subtract 1, always computes something which is greater than or equal to the function which computes the natural log. Okay? So that's why I've done the last bit of this approximation. So I see that my error bound, when I go out to something like 1.0001, is just that 0.00001, however many zeros it has. Okay? So this justifies the error bound from the first video with a little non-calculus explanation. Hope you enjoyed it.